Good afternoon, everybody. Welcome back to lecture number
38.
38. Today we will cover the universal, we'll start the fifth module. What's the fifth module? Special machines. Special machines, there is lots of special machines. If you look at this diagram, we had a similar one in module 1. But the special machines are stepper motor, brushless DC motor, hysteresis motor, switched reluctance motor, universal motor. These two motors are not gonna covered in this course because one is that they are a little bit advanced. They involve DQ transformation, especially I'm talking about the reluctance motor, switched reluctance machine. Switched reluctance machine is probably now the end of the research. Now, if you want to do research, if you want to build a new machine, nobody is building a new universal machine, or a new induction machine, or a new permanent magnet, or a new brushless DC motor. All of the research right now is going to the switched reluctance machine. Basically, based on the rotor position, the reluctance, which is what is the reluctance? Do you remember the magnetic circuit? It's like the resistance, but in magnetic circuit changes based on the speed, based on the electric current, etc. And that's how they control the machine. Of course, it involves power electronics, and there is electric cars, they use switched reluctance machine. Switched reluctance machine is equivalent of induction machine, but in synchronous. Think about synchronous machine, but the rotor side doesn't have windings, doesn't have excitation. Its excitation comes from switching the reluctance. It's a special design. Some of them come in triangle shapes, some of them come at very different things, and of course it involves permanent magnet, etc. But switched reluctance machine is probably right now, and it's exploded in the recent 10 to 15 years, not that much. And the universal machine. In this course we already covered brushless DC. Brushless DC is nothing but a synchronous machine, regular synchronous machine, plus power electronics, where you get it from DC supply. The stepper motor, we will cover it, and we will cover, what else we'll cover? Oh, single phase induction machine. So in this chapter, in the special machines, we will cover, you can add here, one phase IM. Single phase induction machines, we're going to cover them because they are very common. We're going to cover universal machine, and we're going to cover stepper motor. So we already played the video. So what is the principle? The principle for universal machine or universal motor, does it make sense to have a universal generator? Think with me. We already watched in the video that the whole idea behind universal motor or machine is you give it either DC or AC. It doesn't matter. It will work both ways. So it doesn't make sense to call it universal generator, because if you apply the rotation, it will be what? A DC generator. Get it? Because the whole structure is series DC machine. It's just a series DC machine. The only addition, laminated stator. In DC machines, did we talk about lamination?
No.
Lamination basically slicing the stator. Lamination is what?
Slicing this state.
We do not slice DC machines because we don't have eddy current losses. Eddy current losses appear only on AC machines. However, if you apply an AC voltage across that series DC machine with lamination to avoid eddy current, it will rotate but at a lower speed compared to the DC machine. How do you remember that when you study? When you study, think with me. Is the DC, do you remember the EE230? You remember I'm talking about DC, and we're talking about AC, and we come up with RMS, which is 1 over square root of 2 of the peak. Do you remember the 1 over square root 2? What did it mean?
Average?
No. Why did we come up with RMS? I'm gonna ask the question to Noah. What is the whole idea behind RMS? EE سكت. ليش اخترعوه؟
Average or?
This side. ليش اخترعوه؟
يعني كأنه average.
كأنها average. Average of what? Good. Average of what? Good.
Nice power.
Power. Thank you. The 1 over square root of 2. If you replace this AC with 1 over square root of its DC, and you calculate the power equal V times I, you will get the same power as if you do the whole calculation in AC. Let's say you have a voltage here. Let's say you have a current here. If you apply VNI, 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 VNI across all the time, if you apply the VRMS, and let's say IRMS, if you multiply them together, the average power here, would it be equivalent to the average power across the sinusoidal side? Now, for the same DC that its peak, let's say 120 volts, if I have an AC that has a peak 120 volts, what's the RMS?
Yes.
120 over square root of 2.
Yes.
So the power of that, is it larger than the power of this?
Usually lower.
No, because the RMS voltage is lower. So that's why, think with me, that the universal motor, if you apply AC, it gets less power. Okay? We will see the calculations behind that today. So it is a single phase, series motor. We can apply DC or AC. مش معناته إذا حطينا AC إنه ما راح يشتغل. If you apply AC to any DC machine, it will rotate. It will rotate. However, if it's not designed well, it will rotate and stop, rotate and stop, rotate and stop. DC, if you apply a DC voltage, it will rotate regularly. AC, it has to do some changes, including the lamination. This is a very widely used in fractional horsepower. إيش معنى fractional horsepower? Think with me. I'm gonna ask Ahmed Ibn. وإيش معنى fraction?
Less than the horsepower.
طيب يعني وإيش معناه؟
Fraction from the horsepower.
طيب
ربع حصان بس.
ربع حصان يعني السيارات كم حصان؟
ها؟
السيارات كم حصان؟
احسن كثير.
أحسن كثير معناته إن هذا أحسن يعني ربع حصان يعني صغير ولا كبير؟
صغير.
So fractional, it's a small. Do not use it for high power. That's the idea. Do not use. يعني كنا يقول لا تستخدمونه in high power. So we don't expect to see it in EVs. We don't expect to see it in EVs. However, we see it in drills, mixers, خلاط, vacuum cleaners. Maybe it has a universal motor. Why we have it? We have it because if we put power electronics in the appliance and we ask you, let's say we get the AC power 120 and then we have power electronics, we change the speed, what will happen? We add cost. Power electronics are not cheap. Same with the argument of computers. What is the most expensive part of the computer? Let's talk about
Processor.
Let's talk about the MacBooks. So now there is a new MacBook, right? It's called Neo. What is the chip that they are using? Chip of iPhone. So they put the chip of iPhone inside their MacBook. They were able to reduce the cost compared to Air by 40%. From $1,000 to $600. If you're stealing, you get it for $500. You know that. So by reducing the cost of the processor, what is inside the processor? Transistors. And how big it is?
Nanometers.
How big is the transistor in IGBTs for machines? Huge. So to produce very high power electronics that is capable of handling lots of amps, you need to put money. You need to put money. Now, in IGBTs, how many transistors we put? 6, 7. In the MacBook, millions. In the Windows computers, did whatever, millions. I'm not comparing that. I'm comparing the whole cost of power electronics with IGBTs. They are not cheap. They are big. They are bulky. You need special chemical materials. Okay? That's why we do not put good power electronics in some machines. So it comes some ideas. Okay, let's use the DC machine. Let's put it into whatever AC power supply we have. So that's very important. Cost is the main driver. Okay? So if you want to do it in AC, should you apply, does it make sense to have it a 3-phase or AC or single phase?
Single phase.
Why? Because we only have access to single phase as customers. So can I sell a mixer and I tell the user you should have a 3-phase power? That doesn't make sense. Vacuum cleaner? No. It has to be single phase. So it should include some small power electronics, not the expensive ones, and it should adapt. DC machines are also cheap to manufacture, similar to induction. Universal motors, remember we talked about the lamination. Now there is some old, it's not anymore used in some truck applications, they used universal motor, AC excited. Probably if you remember, يعني, there is some, how can I say, there is some old trucks that have cranes that instead of the hydraulic system they have DC machines or universal machine, but it's not used anymore. There is more better machines to be used. Now, if you apply, I'm telling you it's a serious DC machine. If you apply DC, do you remember these equations? These equations are nothing but the equations for DC excitation, and we had this KSIR, IA, omega M for EA, and we had the equation for the torque KSR I squared, and we get the speed control. How did we get the speed control? It's VT over K IA minus the summation of the resistance. If you had a variable resistance RAE, if you increase it, you can reduce the speed and torque. You can operate at a different speed torque. So I'm not going to talk about the DC part. Let's see what will happen if you apply the AC in the series DC motor with lamination. So if eddy current effects are neglected, why we neglect eddy current effects?
Laminated.
Because we already laminated. Without lamination, you have to include it. After lamination, losses become more or less? Less. So let's say we're going to ignore these small losses. But keep in mind, if you work with ANSYS, for example, or any finite element analysis software like Maxwell, there is lots of, I wanted to give it to you in this semester, but there was a reluctance from your class not to have it. There is, if you want to simulate a machine, you should have, I encourage you to look at some YouTube tutorials how to simulate machines. You would notice that always in the model, you have to check a box called include eddy current. So if you include eddy current in your calculation, it will add another equation that's a function of frequency square or frequency to the power 1.5. So now here, if you do the analysis using the equation and you go to the software, you have to uncheck it. Okay? This is just for your mind. Would it matter? Yes, it would matter a little bit, maybe 5, 10 watt in your calculation. So, the current IA and the flux phi sub D, what does sub D means?
DC?
No. Remember we talked about salient pole?
Constant flux. Fixed.
Very close. Direct. But it's constant flux. You're right. It's direct and constant flux. Why? Well, this is the machine. at this point, the flux is a fixed number, okay? If you change the angle, so at this point it's the flux. If you have a direct component with the current, let's say the current is going into the page, and you have the quadrature. So at this point it's constant, at this point it's constant, at this point it's constant, and it rotates over time. So it's like a phasor that has a constant amplitude that rotates over time. So that number is constant, okay? But it's a function of time because it rotates with AC. It's like a phasor that rotates over time. So it means this side of the stator, we get the peak at certain time. The peak would go here, the peak would go here, the peak would go here, the peak would go here. To make the analysis easy, you have to have it in two components. One direct with the current, one quadrature with the current. The one that's quadrature, you ignore it because cosine 90 is what? 0. So you ignore it and you focus on the direct one. So can you resemble the AC to Im cosine omega t? So that number, if I is now a number, there is a corresponding flux. So they are proportional. So this is the amplitude, which is constant, that's the max. This is the amplitude. You multiply by cosine omega of t. Cosine of omega of t, I explained to you in E360 if you took it with me. Cosine omega t is nothing but a rotating phasor. So the actual length is fixed. And that peak, depending on the rotor position, would rotate over time. So let's talk about only the components that aligns with IA, which are in phase. This means that the armature current and the included EMF will be in phase. So do you remember this equation for DC machine? So in DC machine we had constant times flux times omega. In DC machine this was a number without cosine. But now this number would change over time. The RMS value of this, take the RMS. If you take the RMS, you divide the peak by square root of 2. And you get that number flux sub D, which is equal to this number, the max over 2. So now, because we took a snapshot, we ignored the fact that AC moves over time, this number now is the RMS, which is a constant value. It's the RMS value of the D-axis flux. We only look at the direct axis. So why am I doing the RMS? We do RMS because we don't want to write this as a function of time. Steep. When you do your calculations, you freeze the time and you take the RMS. Similar argument over here. The instantaneous torque can be calculated by apply the torque equation K flux IA. This is for DC machine. I think we have it. No, we don't have it here. We have it. We had it before. If you do the equation, you will find that the K times the flux times IA. Write the time domain expression. You get cosine squared. One from IA, one from phi sub D time domain, not RMS. Do the trigonometry, math 002. Who skipped math 00?
You can't.
No, who skipped? You skipped? You missed a lot. You missed. If it was up to me, I wouldn't allow skip.
No, but you need to take an exam to skip it.
Yeah, but what's the point? You already took 101 in high school. Then why didn't you skip 101? I think math 02. Okay. Did I tell you about the average joke? You know the average. Major 2002. I got, I think, 8 out of 20. Average was 12. Okay? So you missed the most difficult course. You should retake.
Math is hard, Doctor. Math is hard.
Math is hard, yes. There is some students who rely on math to get partial credit. Not with my class. So 07 is a clear example. If you know nothing but you know math, you'll get A plus. Now, trigonometry, this trigonometry is used for many reasons, but one historic reason is why we get rid of the squares is if you, in the old computers, doing the square operation was hard for memory. That's why they always get rid of the square. And the tradition kept until today. That's one historic reason. Old computers cannot multiply, only add. And they sample, so they put sample. They don't have T, they have a series, and every time they plug the number and they get a number and then they substitute. You cannot do square, multiply, it's complicated for them. The average torque, get the average torque. How to get the average torque? Get the RMS values. No, not the RMS. Yeah, you get the RMS value. So this is the RMS value. Phi sub d, IA, these are RMS. This is RMS. This is RMS. So the average value is actually this number without the cosine. What's the average of cosine? 0. So if you substitute dm over square root of 2, IM over square root of 2, you get these numbers. So you get a similar torque, KSR IA squared. Go to the torque equation for the DC machine, KSR I squared. So we get the same torque. We get the same torque, but where IA and the flux are RMS current values respectively. Let's go to the power calculation. The electromagnetic developed power can be developed by EA times IA. Attendance, please make sure to write your name. The developed torque can be calculated by torque is the power over speed. Now let's see the phasor diagram, which you don't like. So looking at the phasor diagram, what do we have? The long vector, what's the long vector? VT. So VT is EA plus IART. This is IA in phase. Why it's in phase?
Real value, no angle.
No, why IA is in phase with EA? I'm not talking about IA times RA.
The same shape.
Not really. Okay, remember this argument?
Single phase.
IA and the direct flux are in phase. Isn't the direct flux is a result of EA?
Yes.
So because IA is in phase with the flux is in phase with EA, KA and omega are numbers. So the phase of EA would be the phase of the flux. This implies that IA لزوما تصير in phase مع EA. I think my grade was 9, 8. Okay. I forgot, I have to check. This was a nightmare. Because back when students were not kicked out of the university because of the English, if you get average in math 01, 02, you get C. So if you get just below the average, you get 1 or 2 points, and then you go to the D plus. If you get D plus twice, dismiss. Is the system still there?
No, I think now you could do bus.
Yeah.
بالانجلش اللي دي ما تمشي.
That wasn't the math. So I know many of my colleagues, they couldn't continue, not because of the English, because of the math. So Math 02 was a very, very challenging course. I think it's one of the most difficult. I think I skipped English 02. So if you do the phasor diagram, J, xt is this. What is xt? What's the equation? 2 pi f(L). What is f? 60 hertz. So if you do the phasor diagram, where RT is actually RA plus RSR plus RA. The three resistors for the series machine. Let's go to the DC excitation versus RC excitation. Let's compare the performance if you apply AC or DC. And I'm telling you, without a doubt, who's better if you apply the same maximum voltage? DC. The key point is for the same voltage and current, who performs better. The equation for the DC is Ka times flux times omega. The equation for the DC is K times the flux times omega. What did we say about the flux? Take the RMS value, which is a number, not a function of time. Take only the direct component. Don't take the quadrature component. And assume for some reason that it is proportional to IA and in phase with IA. If we apply the same peak voltage, wouldn't we be seeing the same current for the same peak voltage? Let's pretend that the fluxes, even though they are not the same, it's slightly lower. Let's compare the voltage, the ratio of the voltage with the ratio of the EA, not VT. VT is, we're not comparing VT. We already know the relationship between the VTs. I'm cancelling these two. I'm cancelling the flux just to make my analysis easier. Do you agree with me?
Okay.
So let's see what will happen if EA of DC, compare it with the EA of DC, if they change proportionally, the speed will change proportionally. Does it make sense? Because EA is the one that's proportional to the speed, not VT. Let's do the EA for the DC. Isn't it V minus IA RF RA plus the variable if it's not there? Let's call this RT. You can call this RT for the analysis. This is taken from a different textbook. The EA is what? EA is V cosine theta minus IA RF. Let's see it from here. VT, EA is what? It's VT cosine theta minus IA RF EA. So EA is actually this vector. هذا الفيكتور EA. It's VT cosine minus this component. Do you agree with me?
Yes.
الVT يبدأ من هنا ما يبدأ من هنا. الVT يبدأ من هنا. هذا الVT سوري EA. الVT يبدأ من هنا. Take الVT projection على الX axis. It's this vector. Minus IARs. It's this vector. So you get the EA. That's why we had V cosine minus IARs. Clear?
Clear.
Take the ratio, divide by V. If you divide by V, this will be 1 minus IA over V, IA over V. And for some reason, assume that IA over V, the voltage drop across the resistors is much smaller than the supply. Can we do this assumption? It's a small number, very less than 1. So I'm getting rid of these numbers. So I'm getting this important formula. EA DC over EA AC is 1 over cosine theta. What is cosine theta? Is it the rotor angle?
Yes.
No. We got you this time.
Okay.
It's not. Cosine theta, without thinking about machine, what's cosine theta?
No.
E360, what's cosine theta? Power factor. So it is proportional to 1 over PF. What is the power factor? It's the difference between the angles of VT and IA, which is this angle, cosine theta, with the angle between VT and IA. And how do you control this angle? From the supply, and there is the load. So we notice here that the universal motor, if you apply it on AC, the speed is controlled by power factor. That's one key feature about speed control of the universal motor. Are we going to do it? Probably a little bit. So it can be concluded that for the same terminal voltage and armature current, same torque, the speed will be lower for what? This side? This side. Section F. Speed lower for a DC or an AC?
speed lower for ايش؟
الDC ولا الAC?
AC.
Good. The torque speed characteristics, remember this curve at DC, the torque speed curve is this one. For an AC, it's this one. Note that the AC excitation produces pulsating torque, poor power factor, and lower speed as because of the reactance voltage drop produced by XF and XA. This is not relevant to our class directly. But I remember I told you the pulsating torque. Torque is not smooth. How do you get the smooth torque?
Power electronics.
Yeah, but there's a simpler solution. Rather than one phase, you apply
Three phase.
three phase. So this is, do you remember in Unit 360 they told you three phase, it's good for machines?
Yes.
Because it's smooth. So that's what we mean here. AC excitation, which is a single phase, produces pulsating torque, poor power factor, and lower speed as because of the reactance voltage drop produced by XF. So for the universal machine, we have here what? We have inductors. Those inductors have reactance. This reactance has a voltage drop on the AC, but in the DC it's short circuit, except the transient. So at steady state, for a DC we don't care about the X's, but for an AC we have to include all the X's for the DC machine. And this is one other reason why you have voltage drop that's low. Here is a simple example. 120 volt, 60 hertz, 14 horsepower. Is this a fractional horsepower?
No. It's higher than fraction.
ما ناخذها بالملي fraction, but it's a small machine, 120 volts. This is a relatively big. It should be one less than ربع حصان.
What's the point of using universal motors? We are just relying on the DC excitation.
No, they don't rely on DC. There is many applications. One easy thing is if you allow the user to use DC and AC, for speed control they have more options. This is one application. So if you apply DC, you get this speed. If you apply AC, you get lower performance, you get lower speed, but you still can't plug it in your home. If you have application where you have UPS, universal power supply, uninterruptible power supply, or DC power supply, you can plug it. In a standard electrical machines like EE361 or the machines lab, you have AC and DC. So if you apply it for both, it can work. This is a clear application. The other application is you want to mass produce machines. Some applications, they put it for DC,
Oh, okay.
يعني inside the vacuum cleaner. Maybe another not a vacuum cleaner, maybe a small crane,
It's a multi-purpose.
Multi-purpose.
That can be used for it.
multi-purpose. So if they build a machine, they build it and ship it everywhere.
طب دكتور انت قلت انه غالبا يكون حول الربع هورس باور
مش غالبا. This is because for the AC. We don't talk about DC. احنا نتكلم عن we apply AC all the time. If you apply high power, you're going to have very high losses. It's better to go to induction or synchronous. That's the point. But احنا نمشي الأمور لأن at mass producing, let's say 80% of our customers use it for DC, and there is some customers want good price, cheap deals. We give them the 20%. However, those customers, we already know that they are small horsepower. So we build our DC machine, universal machine for small horsepower. If I get a customer who wants AC with non-fractional horsepower, I guide them to another company that produces induction or synchronous. So that's the main reason. And in the old days, DC machines were more available for control. Controlling them was much easier than firing angles. Controlling DC machine is easy, just DC chopper. But controlling an induction machine with synchronous was way more difficult. Now the shift goes, we have more ACs and we almost don't have any DC. That's why I don't like DC machines, but it's good to talk about it. The reason we're talking about, if you go to a power plant, you will find equipment that's 30 years old. You still have to maintain them. We don't want to throw them. So this is a quick example. For AC excitation, get the X, which is 94.25 ohm. Get the calculation of EA, which is square root of BT squared minus IA squared minus IART. It should be 93. For DC excitation, EA is 108. Take the ratio between them. Now for the speed runs at 2000 RPM, is this at DC or AC? This is at the DC. Because we give the rated value for the DC. Okay? Now, if you compare the ratio of the speed, you will notice that the speed is for AC is 1700 RPM, lower by 250 RPM. We will solve this example next time, but I'm explaining it real quick. The power factor is 0.8 lagging, and the output power is 56 watt, and you get the torque 0.3. The last thing I want to talk about, we'll go over the example next lecture, the drive circuit. You can use power electronics still. There is, for DC excitation, we can use controlled rectifiers, DC chopper class E. What's the other class for DC chopper? Class E, the 4-quadrant operation. Do we need 4-quadrant operation?
Maybe.
If you want to reverse the direction of the motor. For AC excitation, AC voltage control with the tri. So you can have controlled rectifier, class A DC chopper, and AC voltage controller, the triac. This is the end of the universal motor. Please, in your home, try to solve this example. We will solve it real quick at the beginning of next lecture, and which is what? Thursday. Now, we still have to do one additional lecture.
Online would be?
Yeah, online. Should we do one this week?
Sure.
Can we do one tomorrow? 12 p.m.?
في لا
What لا؟ should happen.
482 machine.
Who's not available 12 p.m. tomorrow?
Who's not available?
There is the machine is loud.
Okay, خلاص طيب.
Maybe 1 p.m.
بس تقدر تسويها ريكورد يا دكتور تقدر تسويها ريكورد
No, I can't explain to Ghost.
في ناس بيحضرون اللي ما يقدر
Yeah, I will record. No, but I'm not the one to do it 12. What other time tomorrow you want?
I think 1 is good. 1 p.m. 1 p.m.
1 p.m. still in the lab.
2 p.m.
We need one lecture. احنا متأخرين في المنهج. مرة متأخرين.
2 p.m.
ايش؟ 2 p.m. عندنا لاب.
What time your lab finishes? 5? Should we do it at 5 p.m. online? 5 p.m. online, tomorrow we'll have another lecture, okay? 5 p.m. tomorrow, and then we'll go back to Thursday. We have to make a progress. Quizzes. When do you want the quizzes? If you want to leave, you can leave. Next week we'll have fake quiz, okay? What day you want?
Tuesday.
Thursday. Tuesday?
Tuesday.
So Tuesday fake quiz 4, and the last week we will have the final quiz. Okay?
Mini final or لا؟
No. Okay?
دكتور فاهم كومبريهنسيف
ما ينفع يتسجل كلام حق الفن.